test. Testing the audio whatnottery.
This is a test.
I'm Stou Sandalski, and I'm talking today about building autonomous systems with CAN. Oh, oh yeah. So, quick outline. We're gonna have, dude. I can't. Oh, yeah. I'm used to also seeing it on my laptop, which I can't do. Anyway, so quick outline. We're gonna go over some background. Then we'll discuss CANbus electrical interface and sort of the physical interface to it. Then we'll discuss the DroneCAN software standard protocol. And then I have one example. All right. So quick motivation. Let's say you have a bunch of, you're trying to build a drone and you have a pile of electronics. There's actuators, speed controllers for the motors, GPS, various sensors. Also, the flight computer, the thing that actually is like deciding where the drone will go. You might have another thing that's like a navigation computer, obstacle avoidance, or whatever, several computers working together, trying to talk to or control these sensors. And how do you do this? And of course, it's a trick question, right? Because there's like many ways you can do this, and it depends on what kind of hardware you have, its bandwidth requirements, how important it is, etc. CAN, the thing we're talking about today, is most suitable for low bandwidth, sort of near real time. It's not a real time interface, but you can construct things that are close to real time. Near real time for sensors and various controls like these, like actuators, ESCs, GPS, etc. Right. So just some quick background. So we're on the same page. What do I mean by autonomy? Is basically anything that doesn't have a human in the loop. You can obviously use these sensors and devices to build things that have a human in the loop, but either way. And this is the like the nuclear controller, right? All right, so a couple of just small basic things. A bus, when we talk about a bus, it's basically a mechanism for transferring data from one thing to another, right? There's essentially two flavors of them, two general categories. There's probably always a third or fourth one somebody invented, but the main things are, there's a parallel bus where it's sending a bunch of data at once, 8 bits every clock cycle, 8 bits are cycled out. A serial bus, that sends 1 bit at a time. And some of the buses, there's like infinitely many. I don't remember what the XKCD is, but there's many of these standards. Sort of the important ones, or the ones we're all familiar with, would be like Ethernet, USB. These are serial buses, kind of. CAN is a type of serial bus. And then for devices, you can connect it with these guys that we're all used to or familiar with. But there's also, excuse me, there's also when you go from like a vehicle down to the components, you need a way to connect different boards together, and you could pretty much use anything you want. The common things again would be SPI, R2C, CAN, USB, even Ethernet. It just really depends on what you're trying to do. And then for chip to chip, the one I'm missing there is actually most of the chip to chip communication is happening on not with a standard protocol, but with a whatever the vendor defined, like pull pin 3 high, and that happens, something happens. There's a couple of fairly standardized, electrically standardized protocols, SPI and I2C, and CAN in some ways competes with that, but not quite. So super simple electrical bus. It's almost like a treehouse telephone, CAN line, whatever it is. And basically you have, I have a pointer. Yes. So you have 2 nodes, A and B. And the line is this green thing. It's pulled to some kind of voltage like BCC here. And you have a switch to ground. So if you want to send a 1 to this guy, you leave the switch open and it registers 1. If you want to send a 0, you close it, it goes down. Of course, you have to agree with node B on the clock situation. Either you have another line that provides the clocking, or in the case of CAN, and actually I think Siri also, you just agree on what you're doing. Like we agree that every second 1 bit is being sent down the line. Cool. So there's 2 kinds of buses. again, probably 3 or 4, but these are kind of the general families. The one I just showed is a single-ended bus. You have one signal wire going down, and there's a ground reference, and then you just raise it against the ground, send it down, and the other guy registers it. But a cooler version of this, is this not true? If I'm wrong about something, please stop me. So a cooler version of this, a more robust, is a differential bus, which instead of using a single line, you use 2 lines and send the signal positive on one side. So there's 2 lines here, the positive and the low, the high and the low. You send the signal in a positive way on one, and then the inverted on the second line, and then the receiver basically subtracts one from the other, and you get your pulse. Cool. There's a few very nice features about this. One is that when you subtract the signal out here, you also subtract any common noise that the lines encounter, right? Like any EMI is going to affect, if these lines are balanced, and they need to be for like a differential bus like this, any interference that goes through E&M will register the same peaks on both things. So when you subtract it, you not just get a double amplitude for your signal, but you also get no noise, right? Another super cool feature of this is that the EMI coming off the differential bus is lower than a single-ended one for 2 reasons. One is that, well, I'll give you just one of the reasons. Yeah, the main reason is that the interference, because these are they have different opposing signs, the interference is also coming off opposite. So when the lines are, I don't know if the camera can see me, but when the lines are close together, the interference is reduced. And that's why you would see it is running on a twisted pair. Sorry, got to turn on my timer. I tend to either talk super fast on these or way too long, so need the clock. Anyway, and then another neat thing about this is that there's no return current, right? So your signal integrity is actually higher with like this kind of bus. The other thing, oh, sorry. Yeah. So the other, like a neat little feature is also because you're using lower voltages here, right? Like you're not going from ground up to the whatever 5 volts. You go from, I don't know, like 1.8 to 3. So the actual EMI you're putting out is also less, right? Like it's sort of dependent on the amplitude of the signal.
Does that make, since you have a pair going across, does that like negate kind of the need to synchronize the clocks because it's going to be expecting one and one at the same time?
No, you still need the clock because these things are identical. So even if you knew that they're coming identical, you still wouldn't know how long a bit is. Like you need the clock because you wouldn't be able to tell 2 bits from a single bit. And many things use this, like USB uses this, Ethernet, DisplayPort. Like if you can use a differential bus, like you're going to, like pretty much, it's a good, very solid thing. Oh, okay. I totally already forgot what your question was, but like we'll just move on.
I was just asking about whether it's the question.
Oh, it still needs a clock. Oh.
Does the voltage actually go negative, or is it negative 0?
A good question. So it doesn't go negative. In the buses we're talking about, like I can't speak in general about CAN because there's just so many substandards and details that I can't say for sure it never goes negative. For the buses we're talking about, it does not. Basically, this common voltage here is something like 1.8. So then it goes up to like 3 and then down to 0.8, something like that. So there's like an offset, but yeah, like in a car, for example, you don't quote me on this, but in a car, this common mode might be like 12 or 24 volts. But most of the transceivers for this thing almost don't care about the common voltage, because when you're using this kind of bus, the ground, not that it doesn't matter, but the ground is way less important. So they use tricks to kind of not worry about the common voltage generally, from what I understand. So basically, this is what the signal looks like when it's just going down the wire. For the single ended above, and the single ended above, and then the differential, you can see that it's exactly identical. This is not what CAN looks like, but almost. I have another slide later. So one more piece of background. When you are changing the voltage in a line, there's some delay in when other nodes see the voltage change, right? It's like light is finite, and the light has a finite frequency. So if you have a very long line, there's going to be some delay there. But also because it's electrical, there's inductance and capacitance in the line. So you have to kind of charge the line up to the voltages. So, and it's extremely important to understand that CAN only works if everybody agrees when about the voltage levels. So you have to make sure the propagation delay is much smaller than the bit length. Does it make sense? Like otherwise nodes they have to agree when they're seeing what they're seeing on the bus. This is not true for everything. If you had like a fiber optic line across the Atlantic, that's just not possible to have it be. I mean, you could. It just the bandwidth's like slow. Cool. So quick background. So now we are talking about the CANbus electrical interface itself. Can you see from me? This is basically a messaging standard designed for automotive, mostly automotive and automation. There's a handful of standards and a bunch of historical nodes that sort of don't really matter. It's interesting, but not relevant. So we're only going to talk about CAN 2.0 A and B. These are, it's called standard and extended, and FD-CAN. It's message based, so everybody on the bus sees all the traffic, and it's sort of designed to where sensors just keep sending their data, their status constantly. You don't have to query anything. You can query, but the goal is to just a message thing. It's multi-master, so every node can send or receive whenever it feels like it, versus, let's say, SPI, which has a single master that has to actually ask each node, or not ask, but give time to each node to do it, to talk. 1 megabit, the bandwidth is about a megabit with the classic, and 5 with FD, and you have 8 bytes of payload and 64 for FD. Also, it has CRC in the frame, so it has good signal integrity. Automotive environment is extremely hostile, right? So this was designed to be very rugged across like many things, like EMI, etc. Did I miss one? No. Oh, arbitration. This is important. So because it's a bus, there's a bunch of devices that are like on it. They have to be able to resolve collisions. Like if two nodes try to talk at the same time, there has to be some way for them to figure this out. And it has a built-in mechanism for this using like an ID field. And this actually, the ID field is the main difference between the two buses, the main difference between the 2.0 buses, A and B. Cool. So quick comparison is a little sloppy, but quick comparison between CAN and SPI, I2C, and serial. And by serial, I mean the garden variety serial you would use for like a GPS or something on a Raspberry Pi. There's RS485, which has very similar capabilities to CAN in terms of many nodes on the same bus, etc. But it just doesn't have as much support, so I'm kind of not. It's a good alternative if you don't need to do drones and you have access to RS485 compatible hardware. But anyway, compared to SPI and I2C, CAN is better because it has longer line lengths. It's multi-master. There's no clock. Oh, one thing about the clock line is generates a ton of EMI because you're constantly just turning on the clock on and off, especially on a wire. It's like, I don't want to say it's bad, but like it's definitely noisy. The cooler thing about CAN compared to SPI and I2C is that you don't just get an electrical interface definition. There's also some data definition, where I2C and SPI, most devices that support it use kind of the same settings, but the register maps are all different and the size of things is different. So if you're looking at the scope, like the oscilloscope trace, you still have to calculate in your head like merging numbers, right? Like everything shows up as bytes, so you have to, if it's 16-bit register, you have to do this conversion yourself. CAN is just what it looks like kind of every time, so you can just decode it. obviously you wouldn't know what the data is, but you can at least know there's 8 bits of data in there. Obviously, the disadvantage would be that it's more complicated, costs more money, and it's, I guess, slower than SPI, because SPI I think can go like 50 megabits. I think there's some of the variants, and it's full duplex. So, but you would not run SPI over wires across the room at 50 megabits. So, and then of course it requires accurate clocks, but that's also not that much of an issue these days. Cool. Some limitations: you can get about 100 devices on the same bus. You can probably do more with a little bit of effort. And of course, it's not like you put 100 and then the 101 kills everything. It's just that the more devices, it will become progressively hard to sort of keep the bus capacitance down and the speeds up. But 100 devices on one bus is like pretty good, I would say. And apparently, I've never double checked if this is true, but apparently you can run up to a kilometer at like 50 kbps. I think that's 50K anyway. Cool. So there's this is what on a bus, most buses have some kind of format for the minimum number of bytes you have to send. There's some kind of format that's called a frame. And this is a classic CAN A frame. And I'll just quickly go over some of the fields that are important. One thing is the bus is idle when both lines, right? We have CAN high line, CAN low line here, and then this is the receiver pin on our processor, basically. And time goes this way. This is from Wikipedia. Also, this figure has been offset. In reality, if you're looking at this on the oscilloscope, these would be on top of each other. And CAN highs actually needs to be less than low or equal for it to be in this idle state. Makes sense? Hope. Right. So normally the bus is idle like this, and when it goes up, which is actually a 0, there's some technical reason for this, I guess, but when it goes up, this is a dominant 0, is when it's a start of frame, and after the start of frame, you have either an 11-bit ID field or 29 for extended CAN. Then there's this, ignore the RTR. I'll ignore these control characters for a second. Then you have the data length field. Why is this drifting? Data length field and the data. So in this case, you have 1 here, so there's only a single byte of data. But if there was more, then they would come afterwards. Then there's the CRC field, acknowledge bit, and the frame, which is all ones, right? And because this frame is all ones, there's an issue, right? If my ID is all ones, then how do you tell the end of frame from the start of from this ID? And the way the controller solved this problem, this is not something you ever have to worry about, except if you're looking at a scope trace. It has to turn on these stuffing bits every once in a while to make sure it's not a sequence of zeros or ones. Right? Okay. There's one more field arbitration. Oh, right. So then this arbitration field is where the collision detection takes place, and I have a second slide that explains it slightly better. There was one more point here. Oh, this is like a reserved field for extending the protocol, and IDE here is if we're using standard or extended ID. Oh, and the last thing is this ACK bit here. When you send a frame out, receivers will set this to 0. Sorry, this will be raised to, I'm looking at the wrong thing. This ACK field is set to 0 by the sender, and receivers will bring it up to 1, or actually, yeah. All right, let me roll this back for a second. When you're sending or receiving, when you're sending data on the CANbus, you're sending 1 bit at a time and monitoring the level of the bus. So you're like, I want to raise the bus. I'm going to get mixed up within the 2, but I'm going to raise the bus and check what the bus status is. And if the bus is lowered, that means somebody else is writing on the bus a different number, right? Does that make sense? No.
So that is for the message that just received it, like before the frame.
No, so like this is, the ACK field is for the sender to know that another node on the network received the message.
Yeah, that
this specific frame. So the reader would be reading, and when it gets to here, they'll erase that bit. Or I'm seriously getting like, I'm gonna get super inverted by this, because you can see that the 0 is actually high and low at the same time. So, okay. So the arbitration, this is the collision detection that I was referring to earlier. And this is basically, we're gonna have to make this diagram work. So this is time, goes this way. And this is what's happening at both nodes and what is happening on the bus itself, right? So these nodes both detect an idle time of whatever number of bits it was. They start the frame and they start writing 0, 0, 0, blah, blah, blah. And when it comes to 4, node 15 writes 0. Node 1 wants to, node 16 wants to write a 1, but when it checks the bus, it notices that it's actually a 0 there and realizes that it lost arbitration. And then stops transmitting.
It's the responsibility of all of the senders to
Yes.
monitor the bits.
Yeah. So it's basically, yeah, it's like how it works. And you're basically depending on that everybody's well behaved. And this is mostly true. Like CAN is very old and the controllers are fairly stable. Like, but still, you're actually depending on like a device not misbehaving. Yeah, it's not really an address. That's why they call it an arbitration field, because some protocols will use it as an ID for a device, but then the protocol we're going to talk about next actually uses it as like a message type field. So, but yeah. Totally lost what time it is, but we'll just go with it. So this is this is a CAN FD frame. It's flexible data rate is what FD stands for. And the way this works is that basically, so this is the lower frame is what we had a few slides ago. This is the standard classic frame. The reserve bit, so there's ID and then reserve bit. When that's enabled, it becomes a CAN frame that has slightly like a few more control fields, larger data field, but it's mostly the same structure. But the important part is that when it says 5 megabits, what is actually happening is the data goes at 5 megabits, but the arbitration and control section goes at normal speed. And the reason is you want, I don't know if you want, but generally it's good to have devices that can talk FD and devices that talk classic on the same bus. But the only way that's allowed is if both are actually using FD controllers. So, and I'll say what a controller is in a second. I think I have a slide later. Yes, because FD knows classic, but the other way is not true. And you can actually, you don't need to, like, as long as you have a FD capable transceiver, you don't actually need to configure FD. Like, you can still speak classic, but this gives you capability to go on FD buses. All right, so what does a physical CAN node look like? Basically has 3 parts. Some kind of thing that generates data, right? Like an MCU, DSP, whatever else there can be. A controller, which generates the frames, does the bit stuffing, arbitration, and filtering. Oh, one feature, I guess I'll mention later, but one feature that is useful, one common feature with this arbitration field is you can filter data coming into your processor. So if you don't care about some specific nodes, then you can just filter them out, or only listen to one thing, or multiple things. It's like a bit mask. So the other thing, I keep pointing with my hand, but and then the third component is a transceiver, which is, I guess, just like any normal telecom situation, you'd have a transceiver that creates a signal on the line. Cool. So this is maybe not a typical, but an example bus you could have if you wanted to. This is the line. The wire is, there's 2 lines, CAN high, CAN low, and there's a 120 ohm terminating resistor on both sides. this is pretty robust, so you could get away with not terminating one end for small buses and things like that, but this is what a well-defined bus looks like. And then here we have 3 nodes. If the there's 3 kinds of ways to really connect this. If you have a microcontroller or something with a built-in CAN controller, then you just slap a transceiver on it and you just go, write some software and then go. And then with something like a Raspberry, like a single board computer, or a microcontroller that just doesn't have a CAN controller on it, you can get an external chip. The one I've seen the most is uses SPI, but there's probably ones that do other things. And then you also use a transceiver. And then for like a PC, you just plug in a dongle, like for any kind of interface. And I'll talk a little more about this in a second. So an embedded solution looks something like this. It's really that, I'm not saying it's super simple, but it's really just these connections. There's a receive, transmit pin. Every transceiver usually has some extra functionality. Like they might have silent mode where it just kind of goes quiet, fault detection, and there's a few other things. Oh, one more little detail. You only terminated the ends of the thing. So this loop one way is to either terminate it with a single 120 ohm resistor across the whole thing, or like a slightly better version, depending on application, is to have 260 ohm connected with like with a little resistor capacitor in there. And I think this is more useful if you are using like automotive or something like that. Yes. So, and how do you talk to this thing? Once you have it physically connected, the software is just going to be vendor specific generally, right? On the microcontroller, but typically they would look something like this. This is for STG4, one of the 3 CAN controllers, FD CAN controllers built into it. Older versions have a different CAN controller that's just as good, I guess. But anyway, most of them look like this. They would have some kind of memory for receiving and sending data. As you can't really read this, but it says acceptance filter. They have some kind of filtering facility in them. And generally, you load your data into this RAM from the processor side and call write into some control registers, and it sends it out for you. There's a lot of automation. There's a lot of, yeah, let's go with automation. There's a lot of automation in the background happening. You can't bit bang this. Like this is not, like it's going to be very hard. Right. So, and if you need an external controller, this is the one I was talking about. It's like MCP 2515. Yeah, it's right there. $10 on Amazon. You just connect the SPI. And actually, I brought this drone I've brought. I don't keep the camera. This drone I've brought. There's a Raspberry in here. There's a Raspberry in here that is connected like this to this quadcopter, mostly for like data collection. Right. And then once you connect this, enable the appropriate driver in the like Raspberry Pi, like the layer, whatever it is. Oh, oops. Yes. It just becomes like Linux. And then on the PC, you need like, this is like one of our dongles, but there's a bunch of clones. There's like an open source CAN USB device called Candlelight. There's 20, 30 different clones for it. OSD based. And there's 2 firmware options. One Linux native, like you plug it in, it's just a network adapter. It's like great. And then one called SL-CAN, which is serial over CAN. This is what you'd have to use on Windows, and it's not great. It kind of works, but it's very laggy. But anyway, these clones are the way to go. If you have like a corporate credit card, Quasar makes like really good adapters, but they're like $300, $400, $500, $600. Right. So once you're connected to like a Linux PC, you just need to install like Socket CAN usually. But I think Raspberry is a different thing. Raspberry has its own mechanism, and it just becomes like a normal BSD socket. I have some code in the next slide, but don't be alarmed. It's C. And one other cool thing is it has a virtual interface, so you can actually, without even a dongle, you can write some programs that use this bus if you're testing software or whatever. And as I mentioned, for Windows, maybe a Quasar adapter behaves like a network. but these candle lights with SLCAN, you have to use a program. Like there's like a the programs have to be designed to work with it. Okay, so I just said it's like a socket. Just a quick little quick C here. To open the socket, all you need is a couple of parameters that are CAN specific. Then you set, this is the CAN device name, CAN0 or VCAN0 or whatever. This is obviously going to be a parameter. Go into the system call and bind the socket. And then you can just, because it's such a simple frame, like it's just a struct in C that you can like load with data or pull the data out. You almost never really have to do this, but I'm just saying it's super easy. You can roll your own protocol. Make sense? Cool. So how do you connect a drone? I kind of cut this off, but this is a poster of one of kind of the main autopilots that you would use. It's right here. This is called, it's called a cube. It's basically just a small processing element that connects into like a carrier board that has all the connectors. If you're building like a big agricultural drone, some kind of surveillance thing, this is basically what you'd be using, this or the Pixhawk. I think it's like an old version of these slides, but either way, you can see how it connects. I'll just go over a few of these. But the motors, I don't know if you guys can see these. The motors are down here. It just has two, and they're connected over a PWM interface into the autopilot with a cable each. Then they have some things connected with I2C, and then the CAN actually is up here. You can see they connected a GPS into like a splitter, GPS and optical flow module, a couple of CAN servos. These are like super hard to find. A couple CAN servos, and it connects to this thing. And then once this is connected, you can enable it into your autopilot software, and it should just take it over. Like you have to program it. But the GPS, I think, is kind of the most common accessory that one would run on a CAN. Right. Okay, so almost done with the physical. What kind of CAN, what do you put in the payload, right? Like how do you structure the data there? Many options, but the main, sort of the most ubiquitous ones are this CAN Open and CIA. They're essentially a family of standards. Like it's not like a one thing. There's a bunch of standards for kind of specific domains and the messages that these devices can speak. This is I don't want to say it's super complicated, but it's a pretty complicated protocol. Like, and you can't just get the docs. Like you have to pay money to this organization, get the documentation. It's and there's also almost no open source stacks for this. So you basically, if you want to write like a controller for I don't know, like a forklift or something, you'd have to license this code from some company or something to drive your device. Like you're not going to go and implement it yourself. Similar situation in automotive. SE has like a ton of standards for all the different pieces of a car. And the ones we're talking about is DroneCAN. There's basically two protocols for drones. The DroneCAN, and I think it's called CIFO, something like that. And then I just put this CubeSat space protocol is almost not a joke. I'm sure it's very serious, but there's a bunch of smaller protocols that will work on CAN that people made up, and they're out there. And you can, of course, roll your own because it's very simple. But then you lose access to like common tools and things like that. So rolling your own protocol is like not really a good idea generally, unless you're like trying to learn or something. But it's like rolling your own encryption or something. It's just like not good. Anyway, DroneCAN. So we're talking about DroneCAN. Any questions about the electrical interface? No? So DroneCAN is like a software protocol that runs on top of CANbus, like a 3-volt CAN. It was originally called UAV CAN V0. I think it was like maybe like a thesis project or something like that for somebody like 20 years ago. At some point, the creator wanted to upgrade it. It's a good protocol. I don't want to say that it's like bad, but there's a couple of things that could be improved. So a V1 was developed by the original creator, but the community kind of kept V0 because it works pretty well. Like it's not perfect. It has some kind of clunkiness in it, but it's widely supported. There's tons of devices. Like, why not just have it? We'll keep using it. So it was renamed for UAVCAN V0 to DroneCAN, and then the V1 became this other thing, Sifal. Most of what I'm saying is pretty valid for both of them, except the difference is Sifal does not have common messages. At least it didn't last time I looked. So what I mean by common messages is if you have an air pressure sensor, you can go on the website for DroneCAN, and there's a message definition for air pressure sensors. Might not fit your design exactly, but it's kind of there and you can use it. Versus Sifal, you'd have to invent your own message. Don't quote me this, but I'm pretty sure. Right, it has. It's been in. So if you're building a big drone, there's two firmwares you would use. One of two, either PX4. This is for a big drone, like a big autonomous ag drone. That's not safety certified. So if you had, you either use PX4 or ArduPilot, and ArduPilot's like a practical, good firmware you can get in there, hack whatever you want in it. It works really well. It's tested, like it flies perfect. PX4, pretty good, but they designed with a lot of software engineering in it. I don't know if that makes sense. Like it's very, I don't want to say over because maybe that's how much engineering it needs or something, but it's very complicated. There's a lot of layers. Like it's essentially, I would say ArduPilot is like a monolithic thing. Like you fire it up, it's a program that runs on the thing, controls the robot. PX4 is like an operating system that runs its own programs on top. And because it's so hyper complicated, sometimes it's like it doesn't want to fly, and you're like, why is it not flying? And you have to go find that it's like unhappy about some sensor calibration. And when I was in Minnesota, like I would spend, just as a side part of that statement here, I would pack all my gear in like it's like -20 or something. I pack all my gear to go to the field to fly my drone. I get onto the field to fly the drone, and PX4 is like refusing to fly because some wire is like slightly loose or voltage drop because of the temperature, and you have to like pack your stuff and like go home. So anyway, I would say use ArduPilot if you're building drones. PX4 is maybe more of a research project, like no disrespect. Similar situation, there's two hardware autopilots that are suitable for like a big drone, Pixhawk and the Cube. And I showed the Cube earlier. Pixhawk is pretty much the same thing, but not a cube. Like it's just a monolith thing. There's a ton of tools, not a ton, but there's a few tools that are useful for dealing with this that just come with it, and libraries for serializing, deserializing messages. It allows multi-frame transfers. So instead of just having one frame, you can send a big file in it. Like it's not something that should be used really, but yeah, supports classic and FD-CAN, and it allows redundant interfaces. So if you had two interfaces on autopilot, you could. There's two ways to configure this. You could either have it redundant to where it's sending the same data twice. So if one gets cut, you still have the other one. And DroneCAN does not support the second mode, but typically these buses, you should be able to configure them as like a critical bus that is like your main things, like your gyro or whatever, and then a lower like the lights or some kind of thing that's, if that bus failed, it doesn't matter. But generally with like big drones, well, it doesn't matter. They're very easy to land, right? Like if there's a problem with one device, you can just like land it and like fix it. It's not like a plane where human lives are at risk, generally. Cool. So DroneCAN, and then the type of devices you can find kind of on the market now are just what you would expect, right? There's some airspeed sensors. GPS is like the most common one. There's the drone ID, like every drone these days. This is why I have not actually flown this one. It doesn't have a drone ID on it. It needs a drone ID broadcast. So planes and the FAA knows like somebody's like flying right there. And then ADS-B receiver is another, that's pretty not super useful, but because if you should not be flying anywhere near other aircraft as a drone, right? So knowing that they're there is not that practical. But either way, some laser altimeters, and there's a few electronic speed controllers that are CAN-based, but they're mostly for cars. They're like very big, and boats and things like that. So anyway, these are devices you can find. And sort of the basic functionality that DroneCAN provides for each node is, each node has a heartbeat and a status that is continuously being broadcast on the network. It has its own ID. And then some of the mechanisms are there's like remote restart. file transfer and firmware updates, which is probably the most important one. That there's a facility you can, from the tooling, just send a firmware file to your node, and of course your node has to take it and write it to the flash. But version checking and firmware is super painful to deal with, so this kind of makes it easier. And there's a bunch of messages for pretty much anything you can think of, but you can also write your own using a custom data definition language that gets compiled. Theoretically, I've never used this part, so I can't really vouch for it, but when you write this DSDL, you could use it in Python pretty easily, but it supposedly generates serialization code too for C. But you can also write your own serialization code. It's very simple. Cool. So this is the software, the node properties from one of the tools. Like when you're connected to the bus, you can click and it will open this. And in this case, it's a stepper controller. But you can see the basic properties like operational mode, mode. So this is it fully operational? Is it in a software update cycle? Is it offline? Then you have health, like, okay, warning, error, critical, uptime, and a vendor-specific code. This is just, what is it, like 8 bytes, 8 bits, 16, 8. There's a bit mask you can broadcast if you want to send some information. For our devices, when that's up, it usually means something broke. Like if a sensor is broken, it will set one of these bits. Then there's another mechanism that you can query the node information, and with that query you get the name. So in this case, this is the name of the node, and you can see it's like Java-esque package, right? And then software hardware version, yeah, you can also get some transport stats, update firmware restart. The second coolest thing compared to the firmware are these parameters. So these are not standard, they're just names. You can make up your own names, but it provides a mechanism for setting and getting these parameters, and you have the normal data types like bool, integer, real, and string. So it's like much easier, like when it's like -20 out there, instead of like trying to plug the programmer back into the device to reprogram some configuration parameter you hard coded in the code, you can just click this and change it. Super awesome. This is like my favorite part because you can change settings so quickly. Right modes I already explained. So a bit about the network format. So this is most of the protocol lives in this arbitration field. This is the, you can see it's 29 bits versus 11 because it's extended CAN. And there's basically 3 frame types, like a broadcast message. So there's a source node ID, message type, I think this is 16 bits, 5-bit priority. So you can see like they are kind of using a little bit of the arbitration field for a hard, for a manually set priority level, and the messages themselves are somewhat prioritized. So like the heartbeat is actually message 1, so it's always the, like no matter what, heartbeats trample everybody else. There's one of these. Then the other type of thing, the other frame is a service frame, similar, except now there's a destination ID. So this is for configuration parameters, firmware, etc. But it has less fields, there's less messages allowed. And then this anonymous frame is used for automatic node ID allocation. Like the mechanism is not that important, but this is the 3rd frame. And actually, when you connect like Wireshark, you can go and find a UAV CAN dissector, and just when you connect with your laptop, you could actually see these frames on the network wire. Oh, one more part. Normally, CAN gives you 8 bytes of payload. UAV CAN uses the last byte to facilitate multi-frame transfers. So you actually, with DroneCAN, you lose 1 byte to overhead. And you know, like multi-frame is good. There's some places where you kind of almost can't do it without it. But the issue is, if you have a multi-frame transfer, like you have 20 frames coming down the line, frame 8 lost arbitration too many times, and now the entire transfer is aborted because the resend failed. Because, right, like your stack can do something about resending the entire frame, but on a slower or very congested network, you like I had one time something was misconfigured and it was firing off like millions of messages constantly, and I was like, all I have to do is just update the firmware with the fixed version, and it just never worked because there was so much traffic. My firmware was getting clobbered. I mean, eventually I got it working, but it was so. I'd say, my opinion, single packet is the way to go. It's better if you had like 20 sensors. It's better to have timestamp sensor in each individual packet and assemble it on your PC versus having some massive thing that's being just clobbering the entire bus. Yeah, so they have a cool little utility called the DroneCAN GUI tool. This is kind of what it looks like. This is for like my pick and place machine that I didn't have time to finish the slide, so you'll never really know about it. But these are the nodes on the bus itself, and if you click on them, you'll get the node information panel I showed a few slides ago. So this is actually like you probably cannot see it, but like this thing says node 60, and if you like, nope, cannot move. Well, whatever. Couple cool things about this is it allows firmware updates, right? Plotting data. It has a generic data plotter built into it. You can monitor the bus almost like Wireshark, better in some ways, worse than others. And there's a few panels like for GPS or ESC where you could like control the thing on your desk, like from this. And all of these things, there's many ways you can do this, but having them all kind of there saves like so much time. Just be able to like, oh, what is the data coming out? I'll open the plotter and plot it super quick. Plotter doesn't save data, that does not save settings though. So if you close it, you have to reconfigure. Yeah, so this is the bus monitor. It just looks like kind of what you'd expect. Decodes the frames. Like if you click on here, it will decode all the values right there. And you can see there's a bunch of, so these messages, the data types, all the standard ones are called UAV dot something, but vendor specific ones are like with the URL. I forgot what it's called. This has some kind of name, this inverted thing. And in this case, are we on time? Oh, almost. Oh, I have 8 slides to go. Right. Oh, so in this case, you can actually see there's a bunch of, I don't know, can you guys see this? Can you make out the text? There's a bunch of these standard messages here. This is also from the pick and place machine. It's firing off voltage levels and temperatures. And then there are these messages here that are custom. And the reason this knows what these custom messages look like is because they're in this DSDL like language. Like the tool will load up the definitions and do it where I don't think Wireshark does. It's like the Wireshark dissector can only kind of do some of them. Right, so the other thing is the connector for it. The original UAV CAN V0 standard called for, oh, oops, well, okay. Called for GST GH4, but with DroneCAN, they changed it to where it's kind of recommended. So you can basically use the D sub 9. This is pretty much what normal CAN uses across devices. And this is a very common connector. I mean, so GST GH for kind of circuits like this, and also this M8. Like you can also use like lemos if you like have the corporate credit card. There's really no reason not to. Right. Oh, oops. Okay. This is a Python. This is kind of some Python pseudocode for bringing up a DroneCAN node on like a laptop. And there's a little bit more code than this, but you can see it's like you want to send this message, you just send it. Right? Trivial. Right. Any questions so far? All right. So I have one example. Oh, I guess the main point here is this is useful for drones, totally fine for drones or any kind of vehicles, but sometimes you can build other things with it, low-grade automation, right? So in this case, this is a Meteor camera. It's like it's supposed to, the goal here, this is my pandemic project. So the goal here was to, you mount it on a roof, leave it running, come back like 2 weeks later, and there's a bunch of meteors recorded for you, right? And or you could take it with you, like we took it to, I don't know where we were, but like we took it up to the mountain to record some meteors there. But yeah, Camino's yellow. So if, I don't know if you can see this, but basically, where is it? This is the camera here. It's just like a little Astro all sky camera. It's water cooled. So it's like the cooling system. There's a Peltier controller in there, and then under here I have like another slide. You can see where the oh, I have it here actually. So this is it's actually like a CCD only. It might be CMOS actually. I can never I always forget the difference, but it's like it's only like this big, and it has a like a wide angle for the entire sky. Oh, I have actually a picture. Well, you cannot really see anything. But if you can, we kill the lights for 1 second? Is that possible? So I don't know if you can tell, but like you can kind of make out, these are like 1 second exposures. You can kind of make out the Milky Way. But anyway, so dude, really? I think it died. Oh no. Was there something else on here? No. Right. So the block diagram for this thing, this is what it looks like. This is when it's finally completed in some time in the future. It's going to look like this. Yeah, the problem with like the main problem with this camera, just as a side note, is actually the USB interface has issues, and the drivers the vendor provides can't pull the data down as fast as it has to be pulled down. So anyway, it's just it's always USBs. Like USB is always the problem. So anyway, so this camera it typically has it's powered by a single board computer, like a Rock 64. Actually, it used to be. Now it's like you run it off a laptop actually. And then the camera is USB 3, SPI to like this external controller, and then we have a power module because like we make them, I put them on like everything, right? It's good to know power consumption anyway. Then there's a gyro compass. It's basically like a fused. It's like one device with a bunch of IMUs and barometers on it. It was meant for drones, but it's in here. The purpose is to provide camera orientation and compass heading, essentially. This is mostly, one feature of this camera was that when it sees a satellite, it reconstructs the orbit and then looks up in a table, and it's like, oh, this is a satellite, I'm going to ignore it. And to do that, you need accurate compass heading, orientation, and time. And so also the bus is connected like a normal, the same GPS as a drone. And this is, I guess I would say, mostly for the timing, but if you have the location, might as well write it in there. Oh, and then this thermal controller, this is basically, oh, I have a picture actually, I need to hold it up. But this thermal controller is like right there, and it has one PWM going into it's like a LED controller development board, evaluation board that I'm using to control the Peltier. Because you cannot control Peltier. You're not supposed to control Peltiers using PWM like directly, like with a MOSFET just on off, because supposedly they get damaged. It's controversial. Like on the internet, there's like many threads fighting about this. And I thought I'd do it the right way. And then there's another PWM output for like a dew heater, because this, did I mention this is cooled? Yeah, so this camera is cooled, a little bit noise reduction, but also keeping the sensor at a stable temperature prevents flicker in your time lapses, right? Because the things will look smoother. And these cameras get pretty hot. And there's another device also on CAN going to this fan controller. Originally, this didn't have CAN. The original iteration only had this gyro compass thing, all like hand-built, talking over I2C. And then I left it out overnight and it stopped working. I guess probably some dew got on or something. But once you have the CANbus on there, it's pretty easy to just throw some extra stuff on top. Yeah, and this is what it looks like that I have here. And you can see this is like a TI LED controller I massacred, but yeah, so that's what it looks like. Oh, super awesome feature of CAN. It's not a feature of CAN, but something you can do with it is basically create your own like little dashboard. So this is using bokeh. There's probably a better way these days, but this is it's like a tool for making dashboards. It runs on top of like Tornado in Python, but it's basically this is a Python node with a little bit of a dashboard. This is for the pick and place machine. I have a similar one for this, but it's just for temperature outputs, and I couldn't find the screenshots. But you can, the cool thing about it is you can literally plug your laptop into the drone, monitor the performance without affecting what it's doing. And the same with any kind of like with the pick and place machine. Oh, if something's not working, plug it in without disturbance. Cool. So that is it. And I guess the conclusion, not saying this is the perfect way to do things, but if you have a bunch of different sensors, you need them to be EMI resistant somewhat and worry about the wiring. Oh, right, because you can chain it. So versus connecting all these point-to-point serial wires, you can have a daisy chain around your quadcopter, whatever, and save a couple grams on wires. But it's not even the weight, actually, it's the more wires you have, more chances that some thing is going to get pulled out of a connector and you have to go home. Oh, yeah, and again, it's designed for like drones, UAS, but anyway, you need to put in a bunch of sensors, it like works pretty well. By test cell, like I have this thing that's a bunch of drone motors, the EDFs connected to suck down power for just testing power modules. That thing has a bunch of CAN sensors on it because why not? Yeah. Oh, if you're building like a mech simulator, giant mech simulating cockpit, this would be the way to go to put all the different sensors. Yeah, that's it. Cool. Thanks. I'm gonna leave it on this one because it's a little prettier. Any questions? Oh,
So back in the socket example you have,
oh,
this unmuted?
Yeah.
In the socket example you have some code to respond to a frame, but how does that work when you have something that is like subframe that you have to twiddle? Like you have to twiddle the ACK bit, right?
oh, the controller will do that for you. So the stuffing, you're talking about the stuffing bit or the ACK bit?
Not the stuffing, but the ACK bit.
Oh, it all does it by itself. Basically, when you receive a frame, the controller will acknowledge reception.
So in that example, is that the Python doing it or is that the interface hardware?
It's the interface hardware.
Okay.
Yeah, it's like a pretty complicated protocol at the low level, but because the controllers do everything, you kind of, it's probably not as complicated as Ethernet. But
and then one more, if I may. You talked about bit stuffing. So how is the value of the bit stuffing bits determined?
So the controller is monitoring what is being written. So when it detects, I don't know the exact algorithm it's using, but when it detects, so we cannot have, let's say, what is that, 7 bits of the same value. So when it's, oh, I see what you're saying because, well, sorry, shit. Which way? Oh, okay. So I'm guessing, because I don't know the exact algorithm, when it detects that these are all zeros, it will put it at 1. And then, I don't know. But I wouldn't say, well, no, not exactly, but the bit stuffing is, it's monitoring how many it has sent, and then it determines based on that if it's gonna add, make it 1 or 0. But I can't tell you that much more than that because, yeah, if these are all a sequence, so can these all become 1? Maybe not. But it's also, the bit stuffing is also something you generally don't worry. Yes. Oh. It's also generally something that the controller will deal with.
You have a question? Yeah. Well, I'm just keep gonna call it the ID, the chip ID. Can
Yeah,
you
it's-
set that, or is that just?
It's totally settable. by you. Yeah, like
And
if
how
you
is that hardware like resistors like you would for I2C?
wait, what do you mean? Oh
Uh,
no, this is
How do
in
you
the
set the address basically of the chips?
so we the C code inside. Oh no, that's not C code. In this, it's basically this is a struct with literally it's just these two members. I think maybe there's like two more, but you just set it. It's like a 32-bit number or something, and you just set it like this and write the frame.
But you didn't do that for your GPS module.
In what
or
sense?
Whatever. How do you set the address for your GPS module?
Oh, you mean the node ID or the address? Because this is so where is it? Basically, the ID, what you refer to the ID, the protocol, the ID is filled with, dude, I need to, okay, sorry. The ID is actually filled with this, this is the contents of the ID field in the CAN frame when you're using the DroneCAN standard.
Right.
It's just,
If I receive a message from that ID, I know it comes from the GPS.
oh, I see what you're asking. Basically, the GPS would be, the GPS node will have some number here, but the way you would know it's a GPS is because the message ID would say like GPS fix message, like UAVcan.GPS fix message, and it will have the data in it. So the device doesn't matter necessarily, it's the message it's sending out. So this ID field in a car, maybe CANbus ID is like sensor ID or something, but in DroneCAN, the ID field is filled with like the message type, basically. And then
so then the source node ID is just meant for handling collisions?
no, so source node ID is mostly for configuring the nodes.
Okay.
But it's not. Oh, or are you supposed to repeat the question? Yeah, the source node ID is not that important in DroneCAN. It's mostly for configuration. You could, the main things are these message type IDs, which is, oh, you know, like, well, let me see. Well, I don't want like, I feel like if I touch it, it's going to get more messed up. But if you go on the website, that's what I forgot to do. But if you go on the website, there's a whole bunch of different messages with different IDs, and then the IDs go in here. I don't know. Does that answer your question?
So if you had like front camera and rear camera,
Mhm.
front LiDAR and rear LiDAR, you'd use the source ID to differentiate
No,
because they'd have the same message type.
no. So then the message itself, like if you had, yes, if you had like a different sensors that are sending the same message, the message itself needs to have something to differentiate them. If you want to know that they're different, right? Like sometimes maybe you don't care, but like with like a GPS, there's only one GPS, but yeah, two power sensors, one would have to have, do I have the, so, dude, why is this getting all over the place? Okay, so these three circuit status are all, these three circuit status messages all have the same source ID, but inside each one, there's actually a circuit ID field that sets the thing, but this is specific to each message. So there's like, yeah, three ways to differentiate them. The message ID, which is these types. This is when I say data type or message type, it's these UAV CAN, equipment power, circuit status. And you know, that's like, let's say message 18 or something.
So it's up to the like message type designer to put a
Yeah.
ID field if they need an ID.
Yeah. Yeah, exactly. For that. Because it's, yeah. Not the
So then, what is the purpose of the source ID field? So they all look like they're unique there.
Yeah, like I would say in for the broadcast frame, it's not, it doesn't really matter. Like you pretty, yeah, it's redundant. So like when you're like looking at power data, for example, most of the time you like write both the node ID and the other one, but if everything's configured correctly, you have circuit status, a circuit ID that should tell you what it is versus the node.
And then who's in charge of giving us a unique source node ID if that is required?
You can't, yeah, so you need it needs to be unique, and generally it's good to set it manually. Like if you have a drone, it's like for the like a pick and place machine, they'll set manually. but it provides a mechanism for automatically assigning them. This is what that anonymous frame is used for. There's like a kind of a handshake, and you're assigned like a but you need a service. So in a drone environment, the autopilot is running a little server that assigns node IDs, but yeah, you'd have to like run it. DroneCAN GUI tool also has it. Yeah. Cool. Let me see if I can. Let's see. I want to see if I can. This. Space. Oh, this could be very dangerous.
Watch your auto.
So if you go to the DroneCAN website, let's see, list of standard data types. So yeah, you can see I like the protocol, it's fine, but it's one of these things where it's not perfect, but it's good enough. So when you're looking at these messages, sometimes it's like I can't actually use this because it doesn't have enough bits, or it doesn't have a field, or it has some like awkward thing. But here's your list of it. It's basically, yeah. If you go to find one, there was circuit status. Oh, this is a good one actually. So this is the temperature, device temperature message. Can we do plus? No. Oh yeah. Somebody's rage quitting YouTube. Okay. Dude, what is happening? Okay, so I'm just gonna put it right there. But so you can see how at the top there's a device ID field. That is how you would tell. Yeah, see, that's what I'm saying. It's just something wrong with it. You have to click. Okay. But yeah, there's you like have a float 16 with temperature, and then a device ID in there. And there's messages like the for circuit status. But you can see, for example, if you need 32-bit temperature for you, like whatever. I don't know if you'd ever need 32-bit, but you wouldn't have it. So you need to make your own custom message. And custom message is pretty easy to make, so not a huge showstopper, but yeah. And let me one more. But yeah, this is basically sort of the glamour shot of the GUI tool. I tried to save this, but they like disabled JavaScript, so you couldn't, or like, oh, no, never mind. I tried to save it earlier, but I couldn't. Anyways, any last questions?
You had a diagram of open drain configuration.
Mm-hmm.
You say you had to pull up resistors. Is that also what the CANbus uses?
Yes, I am like 99% sure. I just could not find a good diagram for it. But I would say I don't know. Like I don't want to. I'm pretty sure it is open collector, but it's open collector actually. I would say I don't know. Let's go with I don't know, because I just don't want to set you on a journey of misinformation. I just used that because originally I was going to compare it to the I2C, but then once I started doing it, I'm like, I2C doesn't even make sense to compare to, because it's like one of many things we would use. Yeah.
Okay, thank you.
Thank you.
Awesome.
All right. Well, thank you so much, man.
Thanks.
Awesome talk. And stand right by me here so the camera stays on. So next month, tune in. Mark, one of our members here, Mark, is